Okay, so that made quite a difference, and on the scope here it made quite a difference too. Let's speed it up here a little bit. So I'll move the grounding point again. Let's see if I can make my camera work a little better here. Okay, so I'll move it off that point. There it is on the chassis. Back on the chassis here. And I'll move it again. There's the real grounding point. So now, you know, this raises a real interesting question, to me anyway. Coming back here, just hang on. Gotta bear in mind, I did get a shock off something like this just a little while ago when I was handling my camera here, and I really don't want to repeat that, but shouldn't be a risk because of my isolation transformer. But now, here's my question. Okay, we've kind of just seen with the oscilloscope that there is a hum between the chassis and the ground of the amplifier circuit itself, this being one of the ground points. So why would they take these grounds here, this wire, this one here, which is the signal coming from the cartridge, and use the chassis as the ground point? Why, oh why, oh why? Now, why not just connect it? You know what? I think I have the answer. I think I am thinking ahead. So I'll finish my question. Why not just ground these to this quiet point here? And the answer is that voltage would then be conveyed along these ground shields all the way out onto the cartridge, and anything else that might get grounded along the way. And that's not a good thing. Thinking hard here on a counter. Count of what? If I had a little schematic, it might just be a little bit more obvious. Why? Then, in a sense, you know, when you connect to the chassis, you are also connecting to that blue capacitor, which is soldered on the outside, and it brings back that question again about why the capacitor is done that way. Now, I've read something about this. I can't remember what it was. I read about it. You can see it quite clearly right there. So I'll bet you, though, if I were to disconnect these two grounds and reconnect them together to this point, that this thing would be hum-free. Okay, let's think about that capacitor now. Hang on. Back up. Back up. Yeah, stop thinking about the capacitor. Let me look at a couple of waveforms here. Relative to the chassis, I still have the scope ground on the chassis. There's quite a hum voltage there relative to the chassis. Now where's that hum coming from? Are these capacitors no good? What are the chances? It's pretty small. Are they installed incorrectly? That's not so likely either. That's extremely unlikely. Just double checking. let's look at the hum values on each of those two capacitors. So, let's go here. Don't see anything there. Now that looks pretty bad, doesn't it? That looks really bad. The other one looks like that. So, I'll show you where I'm connecting. So here's the two capacitors. Positive lead from this one goes here, and that's where we get the really strong chop. And look, I mean, there's the diode right there. And the second one is here. You know, it's insufficient filtration. Insufficient filtration. Insufficient filtering of the power supply. Hard to believe. There's the resistor in between the two capacitors. There's a big dropper resistor there. I believe that's more or less stopping inrush current from blowing up the diode. I think that's what's going on there. So this capacitor is not having a tremendous effect on this output here, which looks like that. Now let's get a voltage. Wait, wow. Everything's okay, don't worry. But let's get a voltage, an idea of what voltage this is. So I'm over here on the 1 volt scale, and it's 3 divisions. So that's like 3 volts peak to peak. 3 volts in 100, 3%. Well, we can take a look at that. Let's do this one. First of all, we'll ground it. Set this up to around 10 volts, maybe 20 volts. 20 volts per inch. And move the line down to the bottom here. And now we're going to put this on DC. No, it didn't jump up very high, did it? Okay, that. Back to ground. Lower it down just a little bit further. Okay, so when I flip the switch from ground to DC, you'll see the DC component on the scope, and you'll see the amount of ripple, and then you can get a perspective on how much ripple there really is there, rather than looking at the magnified ripple, which really doesn't teach us too much about things. So there we go. Okay, so that's the amount of DC. It's not very much. According to this, 2 volts per division. 2, 4, 6, 8, 10, 12, 14. That doesn't seem right at all. I would expect it to be like 125, 130 even. Let us investigate this situation. But just on terms of the hum, that's a substantial portion of this. You know, I haven't done this a whole lot with my scope, so my familiarity with what to expect isn't that great. We'll do this a few more times, so we'll get used to it, and used to what's good and what's not so good. So let's get another capacitor. We'll bridge that one that's in there. Just looking for the right size here. Here's one now. 47 microfarads, 450 volts. So I'll have to clip lead this in. Shut the power off. That clicking noise is the motor the motor coming to a halt. In case you're wondering what that is. So we'll clip in this capacitor. Funny how I've said about it. How many times have I said, oh, it's not a power supply hum I'm hearing. Here I am fiddling around with the power supply. Okay, so this be the negative. We can connect it over here. Because here is the same as over in there. Now we're gonna hold it here, turn on the set so the capacitor charges up. I don't want to have the set on and go bam with it. That's not the best idea. Here we go. Okay. Let things warm up and off. This might be hard for you to hear, but there's a definite reduction in the hum level. The buzz level, though, is the same. So there really is two beasts in here. There's this power supply hum, which we're fiddling with right now. And that hum, see, it's not volume dependent. I don't know for sure you can hear that coming and going. So let's get a look at that on the scope. It's not too dramatic on the scope. And now I gotta get my eyes in the right spot here. That's without it. And this is with it. Still quite a bit, isn't there? So what's that? What that is telling me is that be a little careful with this capacitor here because it's charged up to something. We're going to check that too. Let's do that. Here. Okay, so we want to read the voltage. I'm on the 200 volt scale. 145. So that makes my scope pretty stupid, doesn't it? Because scope, I got some 10 times factor going here or something. I don't think so. I don't think I got that feature on my scope. I don't understand that. Very, very, very poorly calibrated oscilloscope, maybe. Never actually checked the calibration on my scope because I'm usually looking at waveforms and not so much actual quantitative values. Now, How do we get away from this hump? If we ground those two wires, take them off the chassis ground and move them onto the supply ground. I don't know, man. That's a, you know, they've done what they've done for a reason. A reason I don't understand. Okay, so I'll leave my video at this. I'll say, why wouldn't I disconnect the grounds for the two wires bringing the signal in from the cartridge and reconnect them, remove them from the chassis, and reconnect them together onto the circuit ground point? Why would I not do this? And I think the answer is, I'm having deja vu here, right? The answer is, if you put them there, you elevate the shock hazard a big deal. If you put those two grounds there, you actually put the whole apparatus in a position where, because it's an unpolarized plug, you plug it in one way and you could have line voltage on anything that's, you'd have line voltage coming out of the protected area down here up right into the cartridge where people handle it. So what they basically do is they stand a capacitor between the this line voltage problem and the external contact, which must exist. I mean, you're going to fool around with a cartridge once in a while. Inevitably, you're going to touch the ground once in a while. Somebody is. So in order to maintain safety, you put a capacitor in because it simply limits the current flow, especially at such a low frequency like 60 Hertz. And because it limits the current flow, if you do get a shock, it's not going to be something to write home about. Without the capacitor, yes, you might not be writing home, potentially. So capacitor in there, and if somebody cross grounds something, then you haven't connected live to neutral through some pieces of equipment. Obviously this record player doesn't quite qualify, but you think about a guitar amplifier and having a bunch of older equipment of this vintage, you would be connecting the line to ground through that capacitor. And the result of that is not so bad. If the capacitor shorts, then all bets are off. You've got potentially full line voltage on the chassis. If the capacitor goes open, you'll get more and more noise. You get more and more noise. Hey, let's check that capacitor and bridge it. I can certainly see 0.05 on there, so 0.05. 0.05. So I think I just figured something out. Basically, that capacitor is providing a safety ground, if you like, in the sense that inevitably some kind of grounded thing's got to come out of here. Something's got to come out of here that's connected into that circuitry and runs that risk. And the way to do it is to do it through this capacitor. You know, I'm talking too much. Let's just see if we can get this in there. Still don't know why it's soldered on the outside of the box. That's a real curious thing, man. It's a little awkward. Okay, I can do it. It's a little awkward. I'm sure I can get my hand in there. of its own when it comes to focusing, doesn't it? There we go. Okay, so I want to connect this here. Let's turn it up. Oops. Let's get this out of here. So this will be improving the capacity of this capacitor. Cool. There's no voltage in either of those terminals, so I'm not too worried. It'd be pretty noisy though if I hit this one here is the grid. If I hit that, I'll be jumping. I don't know. Just, well, you know what? The heck with going that. Let's just do this way. The tension mounts. Here we go. This time I'm going to do it. Low dB. I cut some of it out. Let's try this other one. Or, you know, all I could be doing here is just quieting down the volume in effect. So let's not get too excited. Connecting to either one, it's the same chassis, so yeah. .05. Try 0.1. 1 is good, 2 must be better. Here we go. So as I increase the size of this capacitor, I'm pulling the potential of the chassis and that point closer and closer together, and reducing the potential difference, which is causing this hum that we're hearing. But clearly the better move for hum would be to move these off, put them right on. What if I took them off and put them on with a capacitor? I'd just be getting rid of this connection to the cabinet. That's an interesting question. Yeah, we should try it. Okay, so what I'm suggesting would be a good move is lift this ground off the chassis and connect it to this terminal through a, I would say, 0.1 capacitor. He is. And we'll see what happens. We'll just do that and see what happens. By the way, there's my glued on sheet. Okay, that's great. Let's I'm not sure I want to try to desolder that. It'd be easier if I cut this up a little bit, leave the tail sticking out to resolder it back later if I have to. Still have enough to work with the capacitor, and the capacitor I will connect to this terminal first. Man, I really hope that this works. So, you know, why isn't it done this way in the first place? Why isn't there, if this is a better way to do it, why wasn't it done this way? And I think the answer is, well, that would have cost another $1.50 for the 2 extra capacitors. because you still got to apply a capacitor to safely ground, supposedly safely. What am I doing here? There we go. I don't like that. Let's try it like this. I think this experience, working on the hum here, and the record player that gave me the shocks the other day, has motivated me sufficiently to figure out some stuff I didn't understand that well before. All this being said too soon. Because I'm living in a world of optimism. World of optimism. Where's my cutters? There they are. There they are, right in front of me. Okay, so we'll nip off this. There we go. That's a little hairy. It's kind of. Got some wild ones there. Okay, put some solder on that. Now, because I've only done one channel, we'll be able to test this one channel and the other and see what difference it's made. And we'll find out if I'm on to something here. We're just going to go into the scrap heap of things I thought would work, but didn't. That's a mighty big scrap heap, too. Okay, power on. Little safety check just before the last switch is thrown. There we go. There comes the hum. Coming out of this channel. And now the other channel. That sounds exactly the same. Yeah, the scrap beep just got a little bit bigger. And what if we connected straight to it? Still hums. Hey, what's that telling me? way off in the wrong direction. Okay, I think I've done enough of this. I'm going to post all this up on the internet and see if any more comments come back on what to try next. Maybe it's just, it's just impossible to get rid of this very annoying buzz. Now bear in mind, the buzz could be very strong in my shop here because it may be actually coming externally from... Hey, let's find this out. A little experiment. I'm going to yank the plug out. The moment the plug comes out, the hum disappears. We know it's something to do with that. If it hangs around, we know it's more like a radio hum being received. Ready? So, ready. Watch, man. Pull this plug out. Listen to the hum. Now the hum went away, right away, but I know the heaters stayed live and there was a little bit of B plus there for a moment. So hum goes away. Hum is coming from the power line, power supply. Oh my god, this little amplifier. Oh man. But you know what? This is simple as where you can make the big leaps forward. I'm hoping I'm leaping forward soon on this.